He is the founder of the Serval Project, an open source project which allows mobile telephones to work without remote carriers for disaster, remote or developing world situations where networks are unavailable, overwhelmed or unaffordable, and usually all three. Like many in the open source community, Paul suffers from a critically high idea flux to available time ratio. His discussion today is entitled Making Mobile Communications Secure and describing them as surprisingly insecure, which is sad considering that good cryptographic frameworks exist. Could everyone please give Paul a very warm welcome?
Welcome all along this morning. Am I on? Can we hear me? Yeah. Good, excellent. I wasn't hearing too much come back. How are you doing this morning? You all moderately slept? Well slept? To the straw poll. So who's well slept? Oh, actually not too bad. Moderately slept? Medium rare slept. Yeah, and that's right. And those in the blue sleep kind of category. Not too bad this morning. So today I actually want to cover a whole bunch of things. So actually a quick straw poll that will be helpful for me. How many of you here have never heard of the Serval Project before in any significant way? Okay, good. Something like about half of you. So I think I've done the right thing by trying to have a bit of general information here as well. Can anyone recognise what this is? Yes?
Right.
That's right, the Mark 1. Yes.
Sonic screwdriver.
Yes. So this is probably about a $9 telephone handset that someone has dutifully removed the standard RJ11 connector, which is such a droll connector because it only fits into one thing. With this much more versatile approach. And without going into any further detail and risk being guilty of promoting crime, that's about all the hardware you need to tap an ordinary landline phone. They're not secure, and of course it's totally analog, isn't it? So once you snip on there, it comes with buttons because the buttons are there so that you can dial using someone else's phone number and call Sweden or wherever you want to call. So landline phones aren't particularly secure. Nor, as it turns out, are our digital mobile phone networks. If anyone is old enough like myself to remember the transition from the terrible old days of analog mobile phones, mine on a full charge could do almost 8 hours. And this whole move to digital because it's secure and better and shinier and yeah, in a pile of ways it is. Unfortunately, the crypto that they put on them was not that great to begin with, and now people can sort of routinely exploit it. So we have this problem that mobile telecommunications is quite vulnerable to intercept in a variety of ways. And so in the Serval Project, where we want to make infrastructure independent telecommunications, we wanted to try and avoid some of these problems. And so we'll talk a little bit more about that as we go through. But the Serval Project itself, we have a very simple mission. We want communications for those in need. And like many good treaty texts and the like, we haven't actually defined precisely what we mean by communications or need. And really we've done it on purpose because sorry, yes, those, yeah, look, it's English, right? There's really not a great deal of precision in any of those words. The quotes, however, are, I think, reasonably accurate and descriptive. But so we really look at need as a whole variety of things, and it was disaster relief that really set us on this kind of mission. And sort of the Haiti earthquake was really a key moment in that, of just seeing and realising the need that would result. But we actually have, again, just as we haven't really defined need, we haven't specifically defined disaster. I work in a university, I'm part of a disaster research institute, and actually getting a definition of disaster out of people is surprisingly difficult, particularly actually inside a disaster research centre where it has implications as to what it means. A common meaning of disaster is actually an event which overwhelms a local community's ability to respond. So if you trip over and stub your toe and need to call an ambulance, and an ambulance is available to come and deal with your toe, that's not a disaster, that's an emergency because the ambulance can come and help. If, however, everyone here at this conference stubbed their toes and all needed ambulance assistance with their stubbed toes, we rapidly find that there were probably maybe a dozen ambulance would be able to turn up fairly swiftly, and everyone else would be left in the misery of their stubbed toes without proper medical support. That would technically be a disaster. And so disasters can be triggered by natural events. So if a volcano were to erupt under this building, that would be a natural disaster. If it erupted under certain other modern architectural buildings, it's probably a little more questionable as to whether it would actually be a disaster. But the point nonetheless applies. But we think about disasters, whether they are naturally caused, whether they are politically caused. You don't need a geothermal volcano to disrupt society. Human beings have amassed a surprising number of ways to actually disrupt human society and safety without having to resort to using geothermal effects. So we have this quite large view of that. And communications we see as being a basic human right, and so anything which impinges on the ability of people to communicate, and we would actually argue communicate privately, private correspondence, is actually impinging their human rights, in particularly in freedom of expression. And the UN has actually kind of backed this up a bit in recent years, which is lovely, despite the fact that other pieces of the UN are trying to prevent private communications. There's wonderful cognitive dissonances that occur in these large organisations and governments. So anyway, what we've set out to do is to say, okay, imagine you're in a disaster, all infrastructure has gone. Perhaps the disaster is that someone actually has managed to make a transporter, and they've actually managed to transport all of us down to Antarctica, and we have no recourse to any infrastructure whatsoever. We want something that can actually still work there to let us to communicate, to send meaningless Twitter messages, and do all of the other things that have become an intrinsic part of modern society. But we're not ignorant of infrastructure. We want to make use of it whenever we can. There's no point, sharing a cute kitten photo on a mesh network if you can't then actually annoy the rest of the global population with that same photo. Or perhaps a little more importantly, being able to get calls in and out and share situation awareness in a disaster out and get information in, weather forecast, whatever the matter is. So some acknowledgements. We have been very fortunate in the Serval project to have support from a number of organisations, totalling, it's now actually a little over $1 million of financial support that we've had, and we are exceptionally grateful to these various organisations. The Awesome Foundation were the first people to back us. If you have a fantastic idea and you need $1,000 in a hurry to make it, and it's something awesome, go to their website. The application process is a web form that basically says our attention span is short, keep your text short, and every 30 days each chapter gives out $1,000 to the most awesome idea that comes in. And of course it's 10 ordinary people who put in $100 a month who judge what is awesome, so it's really lovely. Flinders University, who is my employer and has been for a number of years, they pay me to do all this stuff now, which is really fantastic, and their support is tremendous. The ENONET Foundation have supported us with a number of grants as well. The Shuttleworth Foundation have provided very substantial financial support and other forms of support as well. And more recently, the New America Foundation and Open Internet Technology Project, both of which are very concerned about people being able to communicate freely. And there's a number of other donors and volunteers and our teams. We've got a couple of our developers, Andrew and Jeremy down here, Romana back in Adelaide, Corey, Lynn, a whole bunch of people who without their efforts, we wouldn't be where we're at today. So part of what I'm going to talk about, and the headline for the talk is about securing mobile communications, and in particular looking at our security framework that we've put in. So you can actually, and you're quite welcome in fact, to hop across to GitHub. You don't need a Git account, you can just download the ODT from the relevant place there. This is actually a really, really important point. The more eyeballs we can get on our security framework to look for faults and deal with them, the better, because one day lives probably will depend on the privacy and security of communication over what we're creating. And indeed, one of my key intentions with this talk is actually to try and get that socialised out and start getting to people to look at that. because security it's like building a castle. It doesn't matter how many turrets and and boiling oil pots you have. If someone has the key to the secret passage, then well, what's the point really? So what can the Serval Mesh software do at present? So we have encrypted voice calls, we have encrypted SMS type service which we call MeshMS, and we have a file and data distribution system that we call Rhizome. And they're really the kind of the core aspects of the Serval Mesh software. We then have a nice crowdsourced mapping application that uses OpenStreetMap data. We'll be very much looking forward to the next talk that's in this room, talking about OpenStreetMap use in humanitarian situations. Because we've been using OpenStreetMap data, so using our reliable and infrastructure independent transport, and then using the OpenStreetMap information to support these sorts of applications. And of course, these sort of meta capabilities of having publicly exposed APIs, the whole thing is open source, obviously, and our security framework that we think is actually, until one of you points out a fatal flaw in it, we think is actually a really nice approach to that. And we have fully planned distributed social networking applications. And actually, a bit of a plug on that, we've got something like 1 to 2 dozen of really nicely, clearly defined sub-projects to make the Serval Mesh even more wonderful and amazing. And we would love for volunteers to help us realise some of those things, like for instance making a mesh Twitter type service and then actually tying it into real Twitter. Are things that would be really exciting to see. And if any of you would like to get a higher degree, or just would like the government to pay you a higher degree scholarship while you work on amazing open source stuff, and as a side effect getting a higher degree, being based in a university, we can totally explore that opportunity. And some of you may think that you're not able to get enrolled in a higher degree. Talk to us anyway. I don't have an honours degree, but I went straight from bachelor to doing a PhD. There are ways, and we can look at recognising actual practical experience as well as academic experience to try and make these things happen if people are interested. And you wouldn't have to move to Adelaide either. Unlike Google, we understand the concept of telecommuting. So we've talked a little about our general approach. That we want to make something that is not just a tweak on what's already out there, but actually it needs to be radical and it needs to work without infrastructure. So when we kind of looked around and we sort of saw there's a few things out there that kind of go some way to doing what we're doing, and particularly in the humanitarian space, there's lots of things that they say, oh look, they can work over a 2G network, they can work over only SMS backhaul to work. But what happens when that goes down? Like the Victorian bushfires, the towers were up, but the backhaul was actually gone. And there was no communication available. And this is something that's repeated again and again and again when disasters strike. Or in politically induced disasters where the government just goes and presses the shiny big red button that turns the entire network off. We need to work with zero infrastructure. And so we started thinking about what that entails. And it became clear to us that the existing protocols really were not well suited to these mesh networks, and that therefore there was this justification for us to take a revolutionary path. And I think what we've managed to achieve actually has been a vindication that we weren't completely, well, I was going to say not completely insane, we probably are completely insane, but that we were actually justified in those decisions. So where we're at the moment, that core stack of voice, MeshMS and file and data distribution pretty much work. There's a whole pile of refinement we need to do on it. Like multi-hop voice, we need to do some improvements to routing. This is one of many projects of taking, say, for instance, the Batman or OLSRD routing algorithms, or the nice bits out of all of them, and putting them into our overlay mesh, and I'll talk about the overlay in a moment. The 0.90 release of the Serval Mesh is probably hitting Google Play as we're talking. It may take 12 to 24 hours to go through. Jeremy's just pressed the button, there you go. The release has happened here. The future is being made today. However, you're here at LCA, you don't have to settle for 0.90. We have a pre-release of 0.91 progress that's available that you can, if you wish to, try on your phones and make mesh calls and things. So unlike most classroom situations, here you're actually actively encouraged to play with your mobile phones while I'm talking. So if I hear happy mesh ringing noises in the background, or if people manage to figure out how to send messages or ring the phones that are in my pockets, go for it. And we're actively pursuing what we're calling our 1.00 release. That wasn't a mesh phone, by the way. It's just my wristwatch. So we're pushing on towards a release 1.00 where we want all of the functionality that we've already talked about and get away from the need for root and ad hoc on a phone and sort of have a nice sort of seamless experience on a phone that lacks that. There are problems with doing that, some of which we'll touch on, and others of which you're quite welcome to talk to me about after. And again, there's lots of fun development in Java and C and documentation and UI and all sorts for anyone that's interested. So, we don't use VoIP on the mesh. Because we worked out really early on when we went up to Arkarulla in the Outback and were sort of doing our initial deployments trials in 2010, that packet loss and SIP and RTP really don't get along very well. We're sort of we're ringing from one phone to another, and it's like it's not ringing. What is going on? And then at one point I actually didn't hang up the phone that was doing the ringing, and then like a minute and a half later the other phone actually suddenly started ringing. And then it dawned on me that packet loss and retries were not particularly optimal. And also, if you want to have encryption and security on SIP and RTP, it's kind of based around this whole central security certificate model. And you go, well, where's your CA when you're in the middle of nowhere and maybe it's just two people with two phones communicating? And also, if we actually do VoIP, that means we need IP, and that means we need to have IP allocation on these networks. And that actually gets quite problematic if you want full mobility. So who here knows about the birthday paradox? Yep, a reasonable number. Who's never heard of the birthday paradox? So how many people do we think we have here in the room?
70.
70, excellent. The man's already been counting. So there is something like a 99.998% chance that there are two people in this room who have the same day and month of their birthday. In fact, with 70 people here in the room, there's actually a good chance that two people actually share exactly the same complete birthday. Translating that over to the mesh, if you have a slash, like if you have 8 bits of network address space available to you, so a /24, after about 16 devices randomly picking their network addresses, chances are two of them will pick the same address. It's really, really annoying. Because even if you have, like 10/8, you can have, about 4,000 devices before they're going to start having clashes. In fact, even if we had all of IPv4, we actually kind of still have a bit of a problem. And so we wanted to get away from that. And also, just avoid a whole pile of the auto configuration issues on there. And also we wanted to get away from the loose coupling between IP address and entity of this whole, like IPsec is this huge, big, complicated monster that causes endless hurt and pain to those who try and set it up. We wanted to completely avoid that and just have the trust relationship built in. And IPv6 isn't actually a good solution either. So, if we say there's, 4 to 8 billion people in the world at the moment, so 2 to the 33 people, Internet of Things means that there's probably going to be more like, we should be designing for, say, 2 to the 48 devices. And that suddenly means that we actually need, potentially 2 to the 96 addresses. But IPv6 actually only has 64 bits of host address. And so you still have this kind of issue, and you end up with packet headers the size of a small planet, and it still doesn't solve this security coupling issue. You still need to have an IPsec or something, and that means you need central certificate authority, and it's just not that ideal. Basically, we could make better use of the same number of bytes. Some other interesting things, you kind of go, well, if we're moving away from IP, that's going to cause a whole pile of legacy application support problems on the mesh. You're absolutely correct. That's a design feature. Because it means that it's much harder for people to actually fill the mesh network with lolcats and everything else. And Windows machines, announcing NetBIOS and goodness knows what else. We're making it an opt-in to make use of the mesh. And we think that that's actually a really good idea. And also if ad hoc Wi-Fi, really, really annoying interoperability problems. So, if you have a Samsung device and an IDEOS device, you have to turn the IDEOS device on first before the Samsung if you actually want them to mesh. And then some devices, broadcast packets will go over ad hoc, but unicast won't get properly delivered, like in that situation. And it was never properly standardised.
Properly standardised, they just didn't implement it as standard.
Well, actually, the standard doesn't fully describe sufficiently. And of course, the standard is suboptimal. Their idea of, the IEEE's idea of an ad hoc Wi-Fi mesh was definitely no more than there are people in this room. Ideally, actually, 3 or 4 people just trying to share a lolcat photo or, I don't know, share an ad from one of their favoured vendors or something. Wi-Fi is absolutely fantastic, don't get me wrong, but it's just, no one saw a commercial value in ad hoc, and so it's kind of, it's moved back in the standards process and doesn't really have anyone driving it. But as I've hinted at already, if we can actually replace IP addresses with something which actually gets us baked-in security from the base, then that's a much, much nicer thing. And so what we have done, in fact, is we're using 256-bit elliptic curve public keys using the NACL crypto library, crypto box keys primarily. So your network address is a public key, and we tunnel this in IPv over IP or anything else. So we don't have any IP address challenges. In the worst case situation, we can in principle have a global scale mesh where everyone had exactly the same IPv4 address, and our mesh would actually still work. It would just do broadcast packets, everyone would receive them because they're on the same subnet, and life would be fairly happy and wonderful. Not counting the fact that broadcast over Wi-Fi actually has a whole pile of fun problems of its own. And 256 bits gives us more than enough scope to deal with this whole birthday paradox problem. It means that we can have something like 2 to the 128 devices on the network. So we can have more devices on the network than IPv6 supports and still be safe from the birthday paradox. And of course, IPv6 couldn't do this because IPv6 kind of needs to geographically aggregate routes. On a mesh, we're freed from that kind of, well actually, we just can't achieve it. And so we may as well have the benefits that come from breaking that symmetry. And of course, because your network address is your public key, you can't spoof. Your device's ID is its public key. You can prove that you own the address. And so it creates a fantastic foundation for everything that we want to do on top of that. As it says, growth simplifications coming up, but I just want to give you some idea of the crypto and how the crypto works. Because I'm saying about this whole thing of the public keys, and it means that you can do this stuff. So how many people here are familiar with Diffie-Hellman key exchange? Okay, how many of you understand how it works? Yeah, not too bad. So we'll cover a little bit more of that. So the crypto that we're using, the 256-bit elliptic curve crypto, has the wonderful property that mathematicians aren't interested in the discrete logarithm problem that underlies it. Mathematicians are much, much more interested in factoring really, really big numbers. Admittedly not prime numbers because they're actually really boring to factor because, well, this is one in itself, right? But numbers that are made of 2 prime numbers are much more interesting to try and factor, assuming that the 2 prime numbers are both really big ones. So what's happened over time is, we've had to go from RSA 512 to 1024 to 2048 and all the rest to get equivalent security. And it's actually, Moore's law has accounted for a bit of that, but not a whole lot. The rest of it is these jolly mathematicians who love factoring big numbers. And so they have made advances. I can't remember the particular, how many bits of security they've worn off purely from their furtive minds being very clever about solving very tricky problems. But as I say, fortunately, very few of them are interested in solving discrete logarithm problems. So at the moment, 56-bit ECC is as good as 3 kbit RSA. I wouldn't mind betting that in 5 years' time it will be as good as 4,000-bit RSA. Not because somehow we'll have got stronger, but because RSA will continue to get eroded because it's based on prime number multiplication and properties. NACL is actually really nice as well. It holds a whole pile of speed records. And when you're talking about $71 phones that you buy from the post office, ooh, did someone just send me something? Maybe. Well done. We'll have to have a look and see in a moment. You might got to one of those phones instead of this phone so far. But $71 phones that have 600 megahertz processors, the speed of crypto is really important. We can encrypt a phone call, so both ways encryption, using about 2% of the CPU on a 600 megahertz phone. We think this is really, really cool. And actually, it kind of says that all modern phones should actually have, like the phone network should support better crypto than they do, because the old argument of, well, look, your average, old Nokia dumb phone could support ROT13 or ROT14 if you're really lucky, is now kind of, I think, out the window. And also NACL, so who here remembers the Sony PlayStation 3 terrible crypto break? Yes. They did a really naughty thing with reusing nonces. The people that wrote NACL, so Dan Bernstein, who's quite a famous crypto guy, who's written this, has gone, yeah, like that's a really, really dumb way to break your crypto. So NACL actually uses a hash of the data you're encrypting as the nonce and does all this lovely stuff so that you don't have to feed in a magic random number to actually get secure encryption that doesn't reveal your private key to everyone. So how does it work? Ooh, now that was someone sending a message through. What does it say? Is it repeatable? That's the first thing. Hoorays for salt. Excellent. Marvellous. So this is very vaguely, but entirely unlike how elliptic curve crypto Diffie-Hellman key exchange works. Ooh, and someone else has sent another one. Hello, everybody. Excellent. Well done. This is pleasing to see, because it says to me that the software we're putting out there actually works, and that people can actually use it without me having to guide them through the install. Okay, so imagine you have a number. So we kind of keep this down to sort of like year 9 algebra. And I understand that may still be grievous to some, and that's fine. There's a whole pile of things that I'm not good at either, so worry not. So if my private key is A, my public key is A multiplied by the number 9. The most accurate point in this statement actually is multiplied by 9. In fact, that actually is how the crypto crypto works. What's not particularly accurate is a multiplied by. So here, multiply is this very special value of multiply for which there is no equivalent divide by. And it's quite bizarre. So that means that you can't divide my public key 9 times A by 9 to work out my private key. Or if you can, then actually you've totally broken elliptic curve crypto, and congratulations to you, you've got a fantastic paper and really annoy a lot of people. So shared secret agreement, so if you have a key, a private key B, your public key is 9B, I know that you've got 9B, I know I've got A, I can multiply them together to get 9BA, which is the same as 9AB. We can each work out that secret, but everyone else can only work out 9A, 9B, which may or may not be equal to 81AB. But what's certainly clear is you can't divide out that extra 9. And so no one else can figure out what's going on. So this gives us end-to-end encryption in every packet. And I can't remember whether I've written it on the next slide or not. No, I haven't. We'll get to this one in a second. But this means that on a serval overlay mesh, unless you specify otherwise, every packet is authenticated and encrypted using this shared secret agreement. Because you don't actually need to exchange any packets to do it. Because you're supplying, like, you say, I want to send a packet to network address blah, and the serval mesh goes, excellent, you've just told me their public key. I know my private key, encrypted packet. Very, very simple. And so we need to keep your private key private, and so we have this lovely keyring structure that can have one or more identities in it. So you can, if you're a sensitive user, you could have a public identity that you really don't care about anyone seeing, and you can have a private identity that you don't want the militia that are about to pull you over to see all the people that you've been talking to in your message traffic. So you might, this isn't in the software at the moment, but it will be in time, and someone can implement it if they would like to, that you can lock that identity and unlock another identity that is completely different. And we're even going to add support for blowing up forever the secret identity when you unlock another public identity, so that you can have plausible deniability. Okay, we are going to go very speedy fast through the bulk of the rest of this. So on Android, we have the serval overlay mesh with our mesh datagram protocol, which is what has this lovely encryption stuff in it. On top of that, we have our voice over mesh protocol, so it's encrypted by virtue of being in that. So you can make phone calls, you can have the peer list, and I'm not actually going to be able to go through all of this because I've talked very wonderfully for a while, but we're going to run out of time otherwise. We can also tie this into OpenBTS. So we're working with the Commotion project to secure communications between OpenBTS open source GSM base stations. This still actually means your communications are wide open over the GSM segment, but we can at least protect the traffic in between them. We have a lovely test framework where we actually test the core servald component, which is actually what does all of the crypto and everything. So Rhizome is our store and forward system that complements MDP. So MDP is a bit like UDP. This is actually, you say, here's a whole file, I want it encrypted or not encrypted, and we do signing of the bundle to make sure that no one can mess with it except for you. And we have a mechanism where you can grow that. So in fact, this MesherMess works by growing a bundle. But we can also store the private key for the bundle, which is a completely separate rolled key, in there in a way that only you, if you own your private key, can extract it. So we don't have to keep even a record of the bundles you've published. This is also really good for plausible deniability. Because no one can look at it and go, well, we can't get your private key, but we know that you made, that bundle that has that cat which has offended, I don't know, dictator X or something. So this is not the current packet format for VOMP, I apologise. But the key point is, because we have all of this lovely crypto baked in from the ground up, we can actually set up an encrypted voice call using two 60-byte packets. And it's very tolerant to packet loss, unlike SIP and RTP, which probably takes something like 10 kilobytes of data to set up an unencrypted voice call. And one of the key things on a mesh network is you need to do preemptive retransmission if you want data to actually arrive in any reliable manner. So unlike SIP, where it sends out one, hey, can you make your end ring every 30 seconds or so? We send them out every 125 milliseconds until the other end acknowledges one, because it's the kind of thing you need to do on a mesh. Okay, we've already kind of talked about that one. One of the secret wrinkles that if you read that security framework document you will discover is that there are two key spaces in NACL. Unfortunately, neither of them can do all of the things we want. One can do public signing, the other one can do everything except public signing. So we have a mechanism where we actually can, using what we call a Hansen packet, which is a please explain request, for translating from one key space to the other. Hansen packets actually appear in other places in the serval mesh as well. So we abbreviate those long addresses into short addresses and we pass around the abbreviations. But if someone needs an explanation, they send a Hansen packet and that gets the full address. And it actually means that we have a more efficient use of space than IPv6, even though we have longer addresses than IPv6. So MDP, we've talked about already. Here's an MDP ping, just to show you. Look, my ping replies are coming back signed or signed and encrypted depending on where they've come from. It's baked into the bottom layer. And look, it says, warning, your ping packet will not be encrypted. It will still be signed, but it will actually be encrypted. And of course, it would be helpful if I could spell in that particular release of the software. So you can have much faith in the quality of our software and the security framework. So in other words, look through it really carefully, because maybe we left the T out somewhere else. Okay, so the MDP packet structure. Essentially we have some header stuff. The recipient and sender fields, they're all variable length because, as was talked about, we can abbreviate addresses and expand those as we have need. We also, the source port and destination port, we allow up to 32 bits. But if it's a low port number, why do we need 4 bytes? We can abbreviate that again using an appropriate length coding field. And so then we use we need a nonce for CryptoBox. This is different to the nonce for the signing, which is what undid the PS3. Reuse of a nonce here only means that if you had 2 encrypted payloads, people could work out the XOR between the 2. It doesn't reveal your private key, which is helpful. Ooh, someone else has sent something. And so then we use a CryptoBox to encapsulate. You can't even tell what the source and destination ports are until you decrypt it. And then we put one or more of these together into an overall frame. So this is for transport over IP. We're going to, and if I actually have enough time, we'll talk about making a mesh helper device that may have RF front ends that are completely different, and we won't do it over IP at all. Also makes our life a whole lot easier. We don't have to write kernel drivers then. It's just, oh, you've given me a UART that talks to a radio. Excellent. I will send packets out in the serval overlay mesh format and do whatever I need with them. Or you could write them out on a piece of paper and carry them to someone else and they could type them in, or have trained squirrels, whatever your preferred mode of network transport is. So VOMP we have talked about substantially already. just again, a comparison of the complexity of SIP versus VOMP. Here's our entire cool state finite state machine. Look, it fits on a single slide, which is a substantial advance on SIP. And here's just an example sequence through. I'm just going to skip over this for now due to time. So authentication of man-in-the-middle attacks. This is a really important piece. If I know your network address, there's no problem for man-in-the-middle. If I don't know your network address, in a disaster situation, we still want to err on the side of letting people communicate. So when you dial a number, it will give you all of the people who are claiming to have that phone number, which we look up via basically a phone number ARP kind of process called serval DNA. And so we have plans to implement some nice mechanisms for, we might show a pretty picture of the same on both phones based on shared secret calculation. It's a whole pile of fun ways to do that. Again, if someone would like to do it, really fun project to work on. But once you have their serval ID, their public key cached, then man-in-the-middle attacks are not a problem at all. Rhizome, we've talked a little bit about that already, and of course it means you can transport data via whatever means you like. But you may laugh at the pigeon and the bicycle. If the pigeon was riding the bicycle now, that would be humorous. However, a pigeon has 2 legs, each of which can carry a micro SD card. Micro SD cards are affordable at 64 gigabytes. Your carrier pigeon can do 100 kilometres an hour over 300 kilometre range. On D-Day in World War II, 32 pigeons made it back from the front lines into the UK within 6 hours, over 400 kilometres. Admittedly, one of them ended up in a chimney and was only discovered last year. But the rest of them made their way through. And you can carry a tremendous amount of store and forward traffic via carrier pigeon.
There's also an RFC on pigeon carrier.
Yes, there is. It would need substantial updating to support this. But again, if someone would like to update the RFC, we've got a fair bit of time between now and April. We could probably squeeze it in.
Jumbo packets.
Indeed, there's a whole pile of fun stuff. So, actually, we did a really big jumbo packet. We actually carried mesh-to-mesh traffic via Boeing 747 from Africa back to Australia to deliver a message into our lab, using no communications infrastructure, just a Boeing 747. But they often can be easier to source in a disaster than a working phone tower. But likewise, people carrying phones around on bicycles or by foot is going to transport the data around. Rhizome we've talked about already a bit. File distribution, yes, we can update the Serval Mesh application over the mesh. In fact, we've done that twice this week already, I think.
Yes.
And you'll probably see more updates come out if you download the one off the QR code at the end of this talk. It will get updated by other people's phones around the place here. This is really cool. It means you can have a disaster zone drop one phone in with the Serval Mesh, and people can copy the software off of that, and then you can put in a single update, and it will propagate through. We have plans to. LimeWire got undone by self-updates. We ask whether you want to do the update, and we have a grant application in to do a quorum-based signing approach. So that if, for instance, we had a nasty court order or someone just flogged our private key that we use for signing the application, once we have a quorum system in place, they would also have to flog some from several other organisations that we will engage with, who will all each have to collectively sign each update of the Serval Mesh. And if they knew that our key got captured, when they put the next update out, they would remove us from the list of authorised keys from that quorum and find another organisation to replace us. We think that's a really cool idea. It's a whole pile of tricky things on there, but distributed trust on a distributed telecommunications network. And we want organisations in countries that do not have mutual extradition treaties. We want resilience at every level in communications. And I have 1 minute left, so this is going to be really, really fun. So Rhizome Security, you can read the document. Serval Map. It's really, really cool. Talk to us about it after. We can put points of interest on a map, share them via Rhizome. And the really cool thing is, meshes are hopeless at getting stuff globally without a backhaul. However, map and geotagged information of use to people in a local area is logically most available to them in the local area via the mesh, because that's where the data is. We can, if you were to fly into an area where people were using Serval maps and you did not have the map for that area, you would soon get the map from the people in that area. And likewise, if they came to your area, it would get copied off your phones. So, we've done some work with New Zealand Red Cross, and we're going to do some more in about 3 weeks' time. Again, talk to me about it. Look, there's some pretty pictures. And we do stuff with Commotion, and we really want to make this helper device that can get rid of all the ad hoc mesh problems by having the RF interfaces on there and do the ad hoc and access point at the same time. And I'm probably out of time, so I'll just keep pressing buttons here. Do we have time for questions or not?